So it's a particular pleasure to be now the chair guest professor, one of the chair guest professors, and can spend more time here. Now, the title of my talk is How Stars End Their Lives. You may wonder, is that a strange talk title? Don't we know how stars end their lives? And to some degree we know, but a lot of it is actually comes from observations. Observations give us a qualitative understanding what happens at the end of the evolution of stars, but there are still major theoretical gaps. And two particular questions I want to address in my talk is not just massive stars, but also low and intermediate mass stars. How do they actually eject their envelopes and become white dwarfs? And this is something that actually applies to stars like the sun. And the second question of interest, where there's been a lot of progress, and I will show you some of that, is how do massive stars explode? I will first give you a little bit of the observation picture, so what some of the key facts we know, summarize some of the basic principles of stellar evolution, which probably is for most of you is not new, and then I will talk about these two specific topics. And in the end, I will show you how we can actually use gravitational wave detections to test some of our predictions. I want to start with this nice picture. This is a collage of so-called planetary nebulae taken from Sky and Telescope, and it's a very pretty picture. Planetary nebula has nothing to do with planets. These are all the envelopes of stars, single or binary stars, that are suddenly ejected. And this is what we think will happen to stars like the sun. So at some point, the sun is expected to eject its envelope very rapidly. And in the course of these planetary nebulae, we often see, or generally see, white dwarfs, which is the remnant of the sun. A white dwarf, and the sun will become a white dwarf of about 60% of its current mass. So somehow it has to lose the other 40%. Now, a white dwarf is an object that's supported by electron degeneracy. As people certainly here know that an electron gas, even at zero temperature, has a finite energy. Finite energy means it provides some pressure, and that can support a white dwarf against the gravitational pull. These occur at low temperature, zero temperature, and so they're permanently stable. Now, the sun, as it will become a white dwarf of about 60% its current mass and will about the radius of the Earth. Now, in this beautiful collage, you see, of course, lots of very interesting and strange objects. We see lots of bipolar structures. And you may wonder, why do single stars eject matter in that way? Well, the reason is most stars actually are not single stars. Most stars are probably in binary systems, and it's due to binary actions that you get these strange bipolar planetary nebulae. Yes, I mean, the sun obviously is not a binary, it's a single star. But of course, if the sun were in a closed binary, it would not have the planetary system and we would not be here. So that's the explanation for that. Now, what these pictures show is that stars at some point start to lose their mass very rapidly. The way that's usually described in the literature is that stars at some point develop a very strong stellar wind, also referred to as a superwind. Now, this is similar to the solar wind, except that it's about 10 orders of magnitudes more powerful. And the sun loses mass in the solar wind, but at the current rate, even over the lifetime of the sun, which is about 10 to 10 years, it will only lose 1 part in 10,000. Now, at the end of the life, these masses will go up by, as I said, by about 10 orders of magnitudes. And so in the time scale of a few thousand years or so, you can lose the rest of the envelope. The question is, why do stars suddenly do this? Now, we get some interesting information by looking at the mass distribution of white dwarfs, which is shown here. Right. If you look at this diagram, this is a recent determination of a histogram of white dwarf masses, and you see this strong peak at about 0.6 times the mass of the sun. And the first question is, why do white dwarfs basically all have a mass very close to this characteristic mass? I mean, you see more massive white dwarfs as well, but there's this very pronounced peak. Now, this has nothing to do with the white dwarf structure itself. You may know that white dwarfs become more massive, and the electron degeneracy becomes relativistic. They can no longer support the gravity, and there's a critical mass referred to as the Chandrasekhar mass, which is about 1.4 times the mass of the sun, beyond which electron degeneracy cannot support a white dwarf. But that's not where you see the peak. I mean, you see white dwarf masses all the way through this Chandrasekhar mass, but there's a characteristic peak. Now, so what we know from this is that stars must increase their mass loss rate at some point and quite suddenly. Now, what happens to more massive stars? Well, that's what happens. They explode. This is a before and after image. And see, there's nothing, not much here initially. And then all of a sudden, you have this bright object, a supernova. Nova means a new star, and a supernova means a bright new star. So all of a sudden, you have this bright new star appearing in the sky. Of course, this is a misnomer because this is not connected with a new star. It's actually connected with the death of the star. Now, this particular example is supernova Fabian already referred to. It was supernova 1987A. It was the last supernova that was visible with the naked eye. Occurred in 1987, and was the first naked eye supernova in hundreds of years. Now, this was particularly important because you see this arrow here, which actually points at the star that exploded. So this is the first time we were actually able to identify the star that exploded. I should point out that this was a blue star. It was not the type of star that people had predicted to explode. So it looked like a middle-aged star. And so this is already one of the puzzles. Why did it explode? Now, this supernova occurred in the Large Magellanic Cloud, which is a satellite galaxy of ours. So it's almost in our galaxy. But in our galaxy, you typically have one such supernova every 50 to 100 years. And there hasn't been one in a while, so we are eagerly awaiting the next one. But of course, there are lots of galaxies. There are 100 billion galaxies in the universe. And so there are supernovae probably tens of supernovae every second somewhere. And there are lots of surveys with which we can actually identify supernovae to quite large distances these days. But the thing we really want is a nearby supernova like supernova 1987A. Now, this is not really the main part of my talk, but I have to slip that in because, as Fabian was alluding to, I've been working on this for the last 36 years, and I'm still working on it, which was a very unusual supernova. But it also was a very useful supernova for understanding what they are. Specifically, one could see about 17 neutrinos coming from the supernova. I will come back to that in more detail later, but these 17 neutrinos told us that what one was seeing was actually the collapse of a core of a star to form a neutron star. And this was really a confirmation of something that has been postulated already in the 30s, but it took till 87 until this was actually verified. In fact, even though these are only 17 neutrinos, you could use them to deduce the energy in that neutrino flux. And that was exactly the energy you expect from the collapse of a core to a neutron star. Now, a neutron star, well, I'll come back to neutron stars later. Now, this was a big success. And I already mentioned that it was a blue star, which is not what was expected. And a few years after the explosion, one could see with HST images this beautiful nebula consisting of 3 overlapping rings. Now, the supernova here is only the little spot in the center. Right? That's the ejector of the supernova. from 1987. This is all material that was ejected not in the supernova, but by the system before. And one can extrapolate back when that happened from the dynamical age, that this happened about 20,000 years ago. So 20,000 years ago, the star, the progenitor, all of a sudden ejected material in a very funny way. This is sort of the geometry of these three rings. The supernova is at the center of the central rings, and the other rings are displaced above and below that ring plane. Now, the answer to that is, and our answer to that is, that this was probably an event that was caused by the merger of two stars that merged essentially 20,000 years ago. If you want more details, please come and see me. Said this is not really the main topic of my talk, but I can show you that we can actually reproduce this triple ring nebula quite well. So it has the right geometry, the right kinematics, and also the right emission strength. There's still some open questions, and at the moment we are actually still working on how this inner ring actually formed. Okay, coming back to stars more generally, you all know one star, the sun. And, you know, it's what we call a self-gravitating object. It's a gravity that keeps the sun together, but it doesn't contract, it doesn't collapse, because it's supported by internal pressure. It's hot inside, and the balance of the pressure forces and gravitational force makes the sun stable. But at the same time, the sun loses energy from the surface. So if there were no energy source, the sun would lose all of its energy in about 10 million years. Now, for a long time, about 100 years ago, that was an issue because one knew that the Earth was much older than that. And so to resupply that energy, one needed an energy source. We all know what that energy source is. It's the nuclear fusion that happens in the center of the sun, where we have 4 protons fusing to a helium nucleus. And that energy is enough to provide the sun, to keep the sun bright for 10 billion years. Now, of course, the sun at the moment is halfway through that nuclear burning and has roughly used half of the hydrogen at the center. So it has another 4.5 billion years to live. But at some point, it will run out of hydrogen. And what happens in the sun and stars more generally is that as soon as you lose and the nuclear burning stops, but you still lose energy, the star contracts. That contraction provides gravitational, it releases gravitational energy, and half of that gravitational energy goes into the radiation, and the other half essentially heats up the interior. So the star, even though it loses energy, becomes hotter, the core of the star. And at some point, the temperature becomes large enough that you can now fuse the helium that you produce in the hydrogen burning. Specifically, you need 3 helium nuclei to fuse by some process to carbon-12. But this, because of the larger Coulomb barrier, requires a high temperature. It's about a factor of 10 higher than for hydrogen burning. And this is the general principle for stars. Stars burn a certain type of nuclear fuel, then they contract till they become hot enough to burn the next nuclear burning phase. Except that for the sun, it ends after helium burning because the sun then develops a degenerate core in the center. And as I mentioned before, that doesn't require any energy source. And so that is stable. At the same time, the star expands and the sun will become a red giant. Now, sun specifically, we estimate will reach a radius that's about 200 times its present radius, which is basically the orbit of the Earth. So the sun will at some point fill all of the sky, and it's a close call whether the Earth will actually be swallowed up or not. Now, the sun then loses its envelope and, as I said, leaves a white dwarf. For more massive stars, and I'm not talking about stars that are perhaps 10 times the mass of the sun, after helium burning, you get another contraction phase, and at some point you fuse carbon to elements like neon and sodium. And after carbon burning, first a short phase of neon burning and then oxygen burning at higher and higher temperatures, fusing heavier and heavier nuclei. But all of that has to end at some point when you have iron in the center. Iron is the most tightly bound nucleus, so you cannot gain any energy by either fusion or fission, and so you run out of nuclear fuel. And if the core at that point is bigger than the Chandrasekhar mass, electron degeneracy cannot support it, and then the only thing that can happen to the core is to collapse. And I'll come back to that later. Okay, so this is a quick introduction, and here the summary of the evolution of stars. I skipped the first phase, very interesting phase, how they actually form out of the molecular clouds, and the two different types of evolution for the low intermediate mass star and the massive stars. The core collapse either lead ultimately to a neutron star or a black hole. Now I want to talk a little about the stability of stars. And you can look at the energy balance of a star. There are two main energy sources in a star like the sun. There's a gravitational energy, potential energy, that keeps the star together. And we can roughly estimate that it's roughly minus gm squared over r times some factor of order unity. You also have the internal energy, thermal energy mostly, that provides the thermal pressure. And I can write this schematically, like some average 3½ kT times the total number of particles. Importantly, the total sum of these two is about minus gm squared over 2r, because this is roughly half the size of the potential energy. So that's the total energy of a star like the sun, and it's negative, which means it's well bound. Now, as you go to more extended envelopes, in particular if you go to big giants, then you also have to think about other sources of energy, specifically the recombination energy. Now that's the energy you release when two ions recombine, for example, a proton and electron forming atomic hydrogen again, and that releases a certain amount of energy, 13.6 electron volts, and that, if you put that into the energy balance, that actually can become important, because with this additional terms, the total energy in an envelope can become positive. Now, what does that mean? You have an object that has a positive total energy. It means if you push it, you can in principle disperse it all the way to infinity and actually release energy. So that's not really a fully stable configuration. I mean, it's stable if nothing happens, because without the recombination energy, this is negative. But if you push it, in principle, you can, well, energetically eject it. This is a fairly trivial point, which was actually already pointed out by Ludwig Biermann in 1938. And he concluded from that if you take very large stars with extended envelopes, they're not stable, they're dynamically unstable and should lose their envelopes. This was 1938. This idea was picked up by Bogdan Pashinsky in 1968. And I mean, he was really one of the masters developing stellar evolution theory. And he was arguing, well, perhaps stars like the giants the sun will become lose the envelopes when the binding energy becomes zero. We rediscovered this a little bit in 1994. This is work with Janren Han, Peter Egel in Cambridge. And we can do a very simple exercise. We can take these extended giants that have a white dwarf core and ask at what point does the envelope energy become zero. And then say that at this point you lose the energy, the envelope, and you're left with whatever core you have at that point. And that makes a prediction for the white dwarf mass distribution. And that's shown here in this solid histogram. And it's similar to what I showed you earlier. There's also a dashed histogram, which shows the observed distribution at that time, 94. And you can see they're practically identical. Now, this was quite remarkable for us because we didn't really put any free parameter in. We just calculate stars and ask when is the envelope energy 0, and that immediately can reproduce this white dwarf distribution. Now, things are a bit more complicated. And I'll come back to them now. We don't really expect that the envelope is just lost in one go, but this is probably the phase when these super winds I mentioned earlier actually start. This was the first calculations, detailed calculations trying to show this were in the late 70s. Do I need to blow it up, or can you need the scaling? This was by Tuckman, and Burkhardt. And what you see here is the radius coordinates for different mass shells as a function of time. So this is a period of 120 years. And this scale here this is about 200 times the radius of the sun, and the top is 1200 times. And you see these really wild radial pulsations. You see a star pulsating here with a radius of about 200 times the radius of the sun, and reaching huge radius. So this is quite dramatic. And this is like having a giant that's the size of the orbit of the Earth, oscillating back and forth to an orbit beyond Jupiter. And it does that every few years. So this is quite dramatic compared to the solar oscillations, which you study here. These are really big amplitude pulsations. Now, what you see here is that these amplitudes build up, and then once in a while you see these every 40 years or so, you see these arrows. This is actually where they found ejection of material, shells of material being ejected. Now, these calculations were very interesting, but they were very simplified. In particular, these were all adiabatic calculations. And soon after, Fox and Wood argued that, well, this is too simple because non-adiabatic effects also have to be taken into account. When the star becomes very large, it actually radiates very efficiently. And it can lose most of the energy that's in the pulsation just by radiation. And they concluded that these mass ejections would not take place if they were properly taken into account. I would still point out that even using the work by Peter Wood and his collaborators, when they claim that you have a superwind, that's exactly the point where the binding energy of the envelope is 0. Well, that's mostly the situation until we started to look at this in more detail again. This is work done by my former PhD student, Matthew Clayton in Oxford. And what he did is a systematic investigation of the dynamical stability of big envelopes in different types of contexts. Now, used a stellar evolution code called MESA, which is fairly standard, but it has the ability of also using and doing hydrodynamical calculations. And yeah. And so that's where the main advance is. Now, I will show you, we've looked at this in different contexts. I will show you first our calculation in the context of what's called common envelope evolution. And I mentioned earlier that many stars are in binary systems. And one of the things that can happen is you have mass transfer from one star to the companion star, but that the companion star cannot actually accrete all the matter, and then it also fills its own envelope. Essentially, what happens is that you have a big star that swallows up the companion star. It engulfs the star, and then you have the core of the star that gives the mass and the companion star, but surrounded by an envelope from the envelope of the giant. This envelope is obviously called a common envelope. And so you have now the core of the star and the companion star orbiting inside an envelope. But if there's any differential rotation, you will have friction, you will have drag. And so the system, this binary system starts to spiral in, which releases orbital energy. And that orbital energy may be enough to actually eject the envelope. And that can produce a Cantor nebula, like I showed in the second slide. And at the end, if you check the envelope, you're left with the core of the star and the companion star, but now in a much closer orbit. So you might start with orbits of years or tens of years, and at the end, you might have periods of a fraction of a day. Now, this is one of the big unsolved phases of binary evolution, and this is one of the focuses of Fritz's work here. The problem is there are lots of length scales and lots of dynamic scales and a lot of physics involved, so that for the time being, for the next probably decade or so, we can't really do fully realistic 3D calculations of this. But we can look at different phases, and I'll show you here one of the work from Fritz's group here of the late phase of this common envelope phase, which shows that you can get the ejection, this bipolar ejection of material at the end. And that looks actually quite similar to some of the things you see in this collage I showed you earlier. Here's an example, which at least optically resembles the observation. Now, this is not what we have done. We looked specifically at the phase, what's the response of the envelope to having a star, a binary system spiraling in. And we do that in 1D. So all the interesting 3D effects, well, are lost. But we can do more physics, can look at all the physical processes that are relevant. And this is typically what we do. This shows the radius of different mass coordinates of a 1.6 solar mass star as a function of time. And we assume that we put in a binary companion, and that binary companion spirals in, shown as the dashed line here, the dotted curve there. And that adds gravity, but also energy to the envelope. And then we show how does the envelope respond. You see it's the surface radius, so it expands quite a bit. And indeed, it goes into this regime where if you calculate the binding energy, it's formally positive. And in 2017, we published a systematic study. We're just looking at these envelopes, putting in energy, which we assume comes from the spiral-in process, and look at what the envelopes do, how do they react. And this is shown here. These are, again, radii, well, it's the surface radius as a function of time for 150 years. And again, you see very big radial pulsations. And this is the blue curve. The red curve actually shows you the mass. So if it's flat, there's no mass loss. And well, here you just get big pulsations, but no mass loss. But as you go to lower energies, you actually start to get ejection events. Every few pulsations, you eject some material, and you can see that in the change of the red curve. So typically, you can lose up to about 1/10 of a solar mass in any of these events. But you can see it's a little bit erratic. It's somewhat stochastic, actually. This is at the bottom. Here we show you long calculation for 1500 years of a 1.6 solar mass star, and it loses mass regularly. Then there's a phase where it doesn't lose any mass, but then it starts to lose mass again and so on. But at the end of this, it has essentially lost all of its envelope in 1500 years. So this is a type of mass loss rate one wants also when one looks at superwind. Now, it's a bit stochastic, and I can tell you that we understand what's going on, but here we'll give you just some clues and a simplified version. Right? If you have a pulsation, if you have regular stable pulsation, you just pulsate back and forth. But here, you have to consider also the role of recombination of hydrogen and helium. And that has an interesting fact. So if you have an extended phase, hydrogen and helium is non-ionized. As you contract and heat the material, it actually ionizes the hydrogen and the helium. But that requires energy. It takes energy out of the thermal energy budget of the pulsation. And but the thermal energy is what stops the contraction. And so by taking that out, you contract more. You get more of a compression because you overshoot because of the loss of energy to ionization. Now then, when you expand, you give that energy back. And that actually gives you an acceleration, it gives you a push. And so this is a classical situation where at some point in your pulsation cycle, you always get an extra push. And that's why you get these growing pulsations. Of course, no, not of course, at some point, the compression is strong enough that when it expands and accelerates the material again, it can actually eject material in one go. This produces these ejection events. This is showing you one of this. I don't want to go in detail here, but this was the pulsation there. And there is, as it expands, you accelerate material and you have this material here. This is all material that's being ejected. As I said, in these simulations, you can eject about 1/10 of a solar mass in one of these ejections. Now, to get these ejections, the pulsation has to be quite coherent, which means that you can't have some parts of the envelope expanding and others contracting, that then you don't get strong compression. And also the expansion can't be too big, because if you become too big, you get this effect that you get radiative losses that completely dominate and take out energy from the pulsation. So similar is to what Bosch and Wood were arguing in '82. Now this is for common envelope systems, but the same also applies to very evolved stars. And here I'm now looking at a star that has finished hydrogen helium burning and evolves as a big so-called asymptotic giant with 1.6 solar mass object. And what you see here is the radius evolution of the star after helium core burning. You see these funny pulsations. They have nothing to do with the pulsations I'm talking about. These are occur on a much longer time scale. The time scale is almost 1 million years. No, it's 1 million years. And this is connected with these stars having both hydrogen and helium burning in shells, but that's unstable, and so they alternate. You have alternations of hydrogen helium burning, and when you have helium burning, you get these short flashes, but the star becomes bigger and more luminous. Now, those details, that's all very interesting. Physics are not relevant for what I'm talking about today, but whenever you have these extensions, the stars go into this regime where the binding energy is actually positive, can be positive, where you can have ejection events just the way I just described before. This is what we show here on the right panel. We show the evolution of the radius and the mass as a function of time during various pulses. In pulse 7, nothing happens, just flat. Pulse 10, you see some radial pulsations, but no mass loss. Still in pulse 12, it's similar. But then in pulse 14, you again get these episodic mass ejection events. And then in pulse 17, it continues. And by the end of pulse 17, essentially you have lost all of the envelope. So this is consistent with this speculation, going all the way back to Paczynski, that this is the point when you get this very rapid mass loss, and primary mass loss we get here can be as high as 10⁻³ solar masses per year. And that this mass loss leads to the ultimate ejection. Now, this is still work in progress because they still have to do some connections to the observations here. This is one of the things I'm planning to do in the next few months. This also happens for more massive stars. More massive stars, this is for 25 solar mass stars, that can also show these pulsations and these ejection events. But it's also of interest to us because it shapes the circumstellar material at the time when stars explode. But this, again, not something I want to talk about today, because the evolution of massive stars is not terminated by the mass loss of the envelope, but it's terminated what happens in the core. And now go back to to the evolution of massive stars. So I told you before, massive stars continue nuclear burning cycles till at the core you have iron, and the core has to collapse if the mass is bigger than the Chandrasekhar mass. Well, it collapses because there is instabilities. The iron starts to photodisintegrate, and then the helium starts to photodisintegrate. And ultimately, you just have, in this collapse, protons and neutrons. And you stop the collapse when you reach nuclear densities. Means essentially that the neutrons touch each other, and the strong force becomes dominant. So at that stage, you have a proto-neutron star, and the neutron star, observationally, has a typical mass of 1.5 times the mass of the sun, but it's only the radius of about 10 kilometers. So it's like taking the sun and compressing it into a volume of the size of Stuttgart or so. Well, these are very compact objects, which also means that you release a lot of gravitational energy. In fact, the gravitational energy that's released in this collapse is actually 10% of the rest mass energy of the core, which is much more than the energy that was released previously during nuclear burning, which only adds up to about 1%. That is a big number, and well, the number doesn't mean much, but it's about more than 100 times the energy you need to power one of the supernovae we observe. So there's plenty of energy, but the problem is that most of that energy comes out in the form of neutrinos. Neutrinos couple very weakly to matter, and they just pass through the rest of the star. And as I showed you earlier, we know this because in 87A, they were actually observed. And for a long time, it was a problem. How could you perhaps tap some of that energy to deposit that in the envelope to make it explode? Because the supernova is an explosion, not a collapse. Now, for several decades, people were actually not able to do that. Sometimes they were, but then when the physics improved, it didn't work again. But there has been really dramatic progress in the last few years. We now have calculations that reliably can explode these stars. And the way we believe this works, and this is a cartoon from the Thomas Janker's group at the MPA in Munich, is that once after you form a neutron star, you still have material falling in, but that at some point leaves the hard surface of a neutron star, so it forms an accretion shock. And behind the accretion shock, we have a relatively high density. And while the proto-neutron star cools and emits neutrinos, some of that neutrino energy is deposited in the region just behind the shock. And if you wait long enough, you may have enough energy to transform that accretion shock into an expanding shock, to revive the shock, and then have that shock move into the envelope and cause the explosion. Now, that's the basic idea. In fact, let me show you simulation. This is a simulation from Thomas Janker's group, which shows you a proto-neutron star just after the initial collapse phase. It expands a bit, and fortunately, you can see there's a faint blue structure outside. That's where the accretion shock is. So now this neutron star cools, and material is still accreted through the accretion shock. And it starts to wobble around a lot. It's very turbulent. The blue object at the center is the neutron star, and this material just behind the accretion shock. This whole phase lasts, in the time scale, 250 milliseconds, which is a long time. It's a long time by dynamical standards because the dynamical time scale is about a millisecond. So it really goes on, and some people have in the past argued that means probably can't work, but it seems to work. After about 400 milliseconds, the shock is revived. And so now there's the movie zooming out to show now how this accretion shock now can expand inside the core of the star. And simulation stops when this outward zooming shock has reached a radius of about 1,300 kilometers. So this is still deep inside the core of the star, but the shock will now propagate into the envelope and eject the rest of the star. And that is a supernova. Right, so this is I think, I mean, not everyone would agree with that, but I think this is the best picture we now have for how supernovae work. It's a threshold process because you need to accumulate enough energy to essentially unbind the outer parts of the core of the star. And I said that the simulations are now successful in producing explosions. Typically, the explosion energy is not yet high enough, not what is actually observed, but I think this will be the final step. At least they solidly explode. Okay, this now leads me to the final part. What's the fate of massive stars? Specifically, what do they form? Do they form neutron stars or black holes? And if they have supernovae, how bright are these supernovae? Normal supernovae or weak or whatever. And this is something we can do for the first time now. In the field, we're actually now in a rather unique situation that we can, on one side, do stellar evolution calculus all the way to core collapse. There's some uncertainties, but in a reasonably reliable way. But we also understand enough about the explosions, if this is the right mechanism, to connect that to the explosion and what's left over afterwards. And this is work that's led here by Fabian Schneider-Hitz, and we started it actually already in Heidelberg. So what we do here is he calculates the pre-supernova structures of different types of stars. And then we combine that with the supernova model that Bernhard Müller at Monash developed. He was a student of Thomas Janka, so he's one of the people who has been doing these 3D hydro simulations, but they're still very expensive. So he has developed a simple parametric model that has all the physics you see in the 3D calculations, and it's also calibrated to explain observed supernovae. So with this, we're in this unique situation that we can combine and make actual predictions. There's other work along those lines, but I think we are taking this a bit further. And this is from a recent paper. Show you we can calculate the structure of massive stars and quantify their properties at the time of the explosion. And for that, we use a parameter that's called compactness, which was introduced by O'Connor and Ott. It's given by this formula. It's m over r in some funny units, but what it actually is just gm over r, the potential energy at a particular mass coordinate, and the mass coordinate chosen is 2.5 solar masses. That sounds a bit arbitrary, and it is, but we actually find that it's not an unreasonable way of quantifying how explodable the star is. So the star is very compact, it has very negative energy. It's much harder to explode it than if it's less compact. And so you see, we can see the compactness landscape. This is plotted here as a function of the core mass of carbon and oxygen. So it's taking off the hydrogen, the helium, because that's more useful. And you see this characteristic landscape. You see, first thing you see as you increase the mass, slowly rise, and then you get this sharp peak. And beyond the sharp peak, it goes down again. Then the higher mass, it goes up again. That's a very characteristic profile. And if you use the compactness as just as an indicator of what happens to these stars, here you have a very high compactness. So it means it's very hard to explode the stars. So we expect black holes, while down here and down here, we expect neutron stars. What I show you on the left-hand side is this compactness shape for a composition that's similar to the sun's. We can also look at a different composition by reducing all the heavy elements by a factor of 10, and we get the curve on the right-hand side. And it's similar, particularly the compactness peak is slightly shifted, but only slightly shifted. At the high masses, things are a bit different, but that has to do with the different mass loss these lower mass metallicity stars have. But the key feature is that this compactness peak seems to be robust and not a strain function of the composition of the star. Now that's the structure, the pre-supernovae structure. We can now use Bernhard Müller's model to predict what the black hole masses are, or neutron star masses as well, but I'm only showing the black hole masses. Ignore the top panel, so we look at the bottom. This is now a prediction of the distribution of black hole masses. And you see this peak around 10 solar masses, which corresponds to the location of this compactness peak. And then because beyond the compactness peak, we predict that you form neutron stars rather than black holes, you get a gap. Right? So that's the direct translation of the pre-supernova structure into the black hole mass distribution. Now, then as you go towards higher masses, get high compactness again, and you get black holes. If you compare the two metallicities, you see at the high mass end things are quite different. That, as I said, has to do with the mass loss. But what I want to focus on is the lower part. You essentially get a peak at roughly the same mass and a gap of black hole masses essentially the same. And that's, we understand why that's independent of metallicity. That is a strong prediction of our models, if you believe the stellar evolution and the supernova formalism. And the interesting thing about this is, of course, that with LIGO, we can actually test that. You know, I think I've heard a lot about LIGO. LIGO is the gravitational wave detector that can detect the mergers of compact objects. And this is shown schematically here. For two neutron stars, you have two neutron stars orbiting each other. That perturbs the space-time. And space-time means you create a gravitational wave, but that takes energy and angular momentum out of the orbit and causes a slow spiraling of this system till it actually merges. The bottom panel, you see the theoretical model, the distortion of the space-time for the last 10th of a second of two neutron stars. And the signal measures actually how a length scale or a time scale changes at time. So if you have delta L, what this essentially shows is delta L over L, the fractional change of a length or time scale. And you see the number we're talking about is 10 to the minus 20. So that's extremely small, and I don't know how they do it, but they do it. So this is for a neutron star. And as you can see, you see the period shortens, the frequency increases. This is actually in a regime which you can make audible. I want to make this audible now. Okay, let's see. I go away. Just converting this signal into acoustic signal, and you heard this character sound, this increase in volume and frequency. That's called a chirp. Now, if you're a musician, you would have known that this was the merger of two neutron stars. If you have two black holes merge, the pitch would be lower, and yeah, you would know that's a neutron star, a black hole. So if you're a musician, you just have to listen to it, and you can make a statement of what types of objects merged. Because this behavior, this increase in frequency, is essentially just a function of the two masses. And it's this combination of the mass of the two objects, which is called the chirp mass. If they are both the same mass, It's basically 90% of the mass of each object. This is something you can essentially directly determine from the observations of the signal. And of course, LIGO has done this. Moreover, LIGO is sensitive to more massive objects, so it's particularly sensitive to black holes. And this is what they published after the third science run. And for this figure, please ignore the solid curve. That's probably not meaningful. Look at the faint individual curves. These are chirp mass probability distributions for individual events. So it's essentially a measurement of a chirp mass with a certain error given by these probability distributions. And these are about 70 or 80 events. And if you just look at that distribution, at the lower end, you see certain things. You see this concentration of systems here, around 8 or 9 solar masses. And then you see a gap between 10 and 12 solar masses. And that is actually exactly what this mass distribution is. Certainly, of course, but this is translating this gives you exactly that. So, in fact, when I showed this recently, someone said, well, so this is, or LIGO already confirms this idea, this theory. You wouldn't go so far. The statistics are still quite bad. But the hope, of course, is that when LIGO starts again in its next science run, 04, which is about to start in 2 weeks, that we get many more sources, many more gravitational wave mergers to really be able to test that prediction. Now, we were expecting perhaps to have 700 more systems. The latest I've heard that LIGO is not going to do as well as hoped for. The improvement is only relatively modest. But nevertheless, even if you get another 100 systems or so, we should be able to make firmer conclusions whether this prediction is right. Because if it is, it would really be strong evidence that our basic picture of the theory of both massive stars and the resulting supernovae is actually correct. And that's what I'm saying. Thank you.